Okay, thank you for the introduction and for the opportunity to speak. So this is joint work with Chris Janjigian and Timo Seppalainen. And so I'm going to be talking about last passage percolation, but let me start with, so I'll start by a motivation that comes from PDEs. Okay, so here's the envisaged stochastic Burgers equation with a forcing term that is, think of it as a random field. And if you take spatial derivative of the u, and you consider that as, spatial integral of the little u, then you get a certain Hamilton-Jacobi Bellman equation. And again, this is the forcing term. You can solve this equation, you can get the viscosity solution using the Lax-Olenek variational formula. So if you give me an initial condition at time t naught, then the way you find the solution at a later time t and spatial point x is by taking a minimum over nice curves starting at time t naught, going to time t, and ending at time t at point x. So you take minimum over, you collect the initial condition at the initial point of the curve, and then a kinetic energy term, it's this one, and a work term. And these two together are called the action functional. And so the minimizing curves allow you to actually reconstruct the solution to Burgers equation. This is the method of characteristics. So the velocity of the minimizing curve gives you the solution to the Burgers equation. Okay, so what I'm interested in is solutions that, so I call them global, but what I really mean by infinite in time solutions to the Hamilton-Jacobi equation or the Burgers equation, which means you take you put initial conditions at time t naught, then you push t naught to minus infinity, and you try to see if there's a limit. And so this is related, therefore, to finding semi-infinite minimizing paths. So paths that start at time minus infinity and go to time t and end at a given point x. And by a minimizing curve, I mean that any finite piece of this curve minimizes the action functional over curves between the two endpoints. Okay, so it turns out that these equations have a certain conserved quantity. So that's the asymptotic rate of growth of the capital U, which I'm calling it asymptotic velocity. And then looking for these by infinite time solutions translates with a certain fixed asymptotic velocity v translates to finding semi-infinite minimizers that have an asymptotic direction as time goes to minus infinity. And so the natural question is, well, are there such by infinite in time solutions? So existence, uniqueness, and stability. So I'll say a little more about stability, but basically what this means is, well, if you put two different initial conditions at time t naught, but that have the same, that correspond to the same conserved quantity v, and then you push t naught to minus infinity, will you get like a unique limit, or will you get more than one limit? Actually, if even with one initial condition, if you push it, will you get a limit, or will you get various limit points? Okay, so these kind of questions have been asked initially by Sinai and collaborators, and then Hanin and collaborators. So, but these were done in settings where the space is compact, or essentially compact, meaning there's some decay, very fast decay in the spatial direction that basically makes the space compact. And these questions are also related to finding invariant measures for certain dynamical systems, something that Freydun mentioned yesterday. And so that's called the ergodic program of Sinai. Okay, so also in a non-compact setting, this has been done by Bakhtin and collaborators, and then Bakhtin himself, for special kinds of forcing that are sums of Dirac masses. Like, for example, the first work with Kator and Khanin was where the forcing is given by delta masses at a Poisson point process. Okay, so all these were done, though, for a fixed value of the conserved quantity. So you give me the conserved quantity, and then I prove results that are valid almost surely, but the null set off of which they might not be valid might depend on the value of the quantity V. So of course, then the natural question is, well, are there such results for all V at once simultaneously? So you throw away one null set, and then you have a result that says for every direction V, there is unique bi-infinite solution that it's stable and so on. Or maybe there are some V's for which it's not stable. So what we do is we study discretization, a discrete version of these equations, and we give actually an answer for all directions at once. Okay, and so along the way, we find some interesting instability structures. So let me show you a picture, an example. So this is the picture that you'd get when you just solve the Burger's equation. These are the shocks. So they are born, and then they evolve in time. They coalesce to form bigger shocks and so on. So shocks actually are points of instability. But when we look in like for random values of the V, what we get is pictures like this. So these are graphs that have bi-infinite paths in them, and they coalesce and branch out. And so we've been calling it the web of instability. So I'll get to that again a little bit more rigorously later in the talk. But let me actually just give you an idea of what I mean by instability and the phenomenon basically that I would like to explain. So in the model that I'll be considering, you'll see in a moment, the space coordinates will be running in the anti-diagonal direction, and the time will be the diagonal direction, but it's going southwest. Okay, so then I'm going to show you a video where. So what is happening in the video? So what I'm going to do is I'm going to do the equivalent in my model, the equivalent of putting an initial condition on an anti-diagonal level. So that's like some initial time, basically. And then finding the characteristic curve that goes up to the points E1 and E2. So my model is discrete space and time, but so think of it as I'm starting at a certain level at a certain time and finding the characteristics up to two neighboring points, okay? And then I'm going to push this level in the northeast direction. So that's like sending time to minus infinity. And then I'm going to just track what happens to the characteristics. So let's see. And on the right, that box on the right is just a zoom in of the little box on the left. And so you see how as the time progresses, as time goes further and further into minus infinity, the characteristics are actually stabilizing, and that they do stabilize in every finite box. Okay, so you see that the picture on the right is not changing anymore. And these parameters here, these are just, think of them as these two H and C are just dual to each other. So like it's enough to keep track of one of them. And they correspond, you can think of it as they correspond to that conserved quantity V. And I'll explain in a moment, like all the connections to the model. So these are parameters from the model that I'll be studying. Okay, so as opposed to So now this is a situation where I picked a direction in which there is an instability near these E1 and E2, like the nearby points. So this is the lattice, and these are E1 and E2. And I'm drawing the same thing as before, the two characteristics. So let's see what happens. So you see they keep switching, and sometimes they switch together to like it looks like they coalesce, but then sometimes they coalesce towards like there's one curve down here and one curve up there, and sometimes they're actually the one from E1 and E2 are to the like they don't coalesce, the two different curves. So this corresponds to having actually, as you solve your equation at this point, you're going to get limit points, different limit points, not a limit for your solution as you push time to minus infinity. So it looks like maybe it's stabilized, but if you wait a little bit longer, see again, it starts over. Okay, so I would like to explain this explain what is going on, at least in my model. Okay, so what is the model that I'll be considering? So that's last passage percolation. So I have, it's two-dimensional. I have the two-dimensional lattice, square lattice. At each point on the lattice, I put a weight. I put a random variable that I'm going to call weights. These weights are going to be i.i.d. They're going to have strictly bigger than 2 moments. And I'm going to assume continuous distribution. So the passage time of a path between 2 points. So I'm only going to consider paths that are upright. So paths that take E1 and E2 steps in this model. And the passage time of a given path is just the sum of the weights along the path. And then the last passage time between points X and Y, well, you maximize the passage time over all paths, upright paths that connect X and Y. So that we call the point-to-point last passage time. And I'll introduce on the next slide actually what a point-to-line passage time is. Okay, so I'm going to call the geodesic a maximizing path. And it's unique because of the continuous weights assumption. And it's not really a geodesic because we don't really like as in the usual, like, we don't have a metric here, but it's by analogy with a different model that's called standard first passage percolation, where the paths are minimizing and they actually are a geodesic because you have a random metric. So this is just by analogy. If you don't like that, just think of them as maximizing paths. And I'm going to be interested in semi-infinite geodesics. So these are paths that start at a given point and just they're upright paths that keep going forever. And each finite piece is a maximizing path between the endpoints of that piece. Okay. All right. So now the point to line is the same idea. You just maximize over. So you start at a given point X and you maximize over all upright paths that go to a given level. And so that's the n that appears in the notation of the point to line. And then you could, if you want, you could also collect at the level, at the end level, you could collect like an end cost. So I chose it to be linear here. You could put any function you want. I chose it to be linear just from the statistical mechanics kind of thinking. This is like an external field. Okay, so what's the interpretation of this? So if you think of space as on the antidiagonal and time going southwest, then you can think of this as this is a linear initial condition put at the initial time, and this is an action function. So this is the work term, and there's no kinetic energy term because all paths, we're on the lattice, all paths have speed 1 actually, so there's no kinetic energy term. And that way this yeah, there you go. So linear initial condition and an action, and then this should remind you of the Lexolanic formula, except we had in there, we have max here, and that's just because of the choice of we maximize over passage times. But I could replace the omegas by minus omegas, then I'd be minimizing, and then it would be last passage, first passage, and then this would be minimum. Okay, so then this you can think of as playing the role, the H is playing the role of the conserved quantity, the V, because it's telling you the linear, like the rate of growth, the spatial rate of growth of the initial condition. Now, both of the point-to-point and point-to-line quantities satisfy an induction equation. And so how do you see this equation? Well, it's easy. From X, whether you're going to a terminal point or to a line, from X, you go to X plus E1 or to X plus E2. These are the only options. And so what you want to do is you want to look at X plus E1 and X plus E2 and see the point-to-point or point-to-line passage time from there and take the largest of the two. And then, because I didn't account for the weight at point X, I have to add it back. And so that's how you get this induction. Okay, so you can think then of this as this is a probabilistic discretization of the Hamilton-Jacobi equation, just because, well, it solves this Laxalenic variational formula. And so I'm thinking of it as a probabilistic discretization of Hamilton-Jacobi. And so it actually even makes more sense if you think about it in positive temperature, so in polymers. So that's something that Ofer explained yesterday. So how would a probabilist discretize the heat equation? Well, you do the Feynman-Katz formula, and then you replace Brownian motion with random walk, and so you get the partition function of a polymer instead of doing like the discrete Laplacian and so on. So okay, so in this sense, this is a discrete version of the stuff that I talked about in the motivation part. Okay, so so the first thing in studying these things is, well, a law of large numbers. So what we call the shape theorem. So this is sort of like the homogenizing the solution to the Hamilton-Jacobi equation. And so what the theorem says that there exists a function that happens to be deterministic. It's concave and one homogeneous on the first quadrant. And what does that do? Well, it describes the linear growth of the passage time, of the point-to-point passage time. And so the basically G0x over L1 norm of x is approximately like G of x over L1 norm of x. And that's in a uniform way. And so why is it called the shape theorem? Because, well, if you look at the sites of the lattice such that G0x is less than some number t, and then you scale by t and you let t go to infinity, this will converge. So what's under this curve will converge to what's under this line. And that line is exactly, what's under this line is exactly the sublevel curves for G, for the shape function G. Okay, so properties of this G are going to be important in what follows. Okay. All right, so a tool that's going to be important in what follows is called the Boozman functions. So what are these? So let me start with the Boozman functions that have a terminal point. So this is just simply gradients of passage times. So the Boozman function is a function of 2 points on the lattice, pairs of points x and y, and you have a terminal point u. And so you just calculate the difference of the gradient of the passage times from x to u minus from y to u. You could do it with point-to-line objects, and so there's a terminal level then, and you could put the linear initial condition also, or terminal condition. So that is the parameter h. And so if you remember that the point-to-line was playing the role of like solving the Hamilton-Jacobi equation, these Boozmans are like they're like gradients. So they're like solutions to the Burger's equation, especially if you look at x to x plus E1 and x plus E2, like the neighboring points. Okay, so what are the properties of these functions? Well, whether they're point-to-point or point-to-line, they satisfy this co-cycle property. That's just telescoping sums. They have a recovery property. So if you give me the Busemanns, I can give you the weights back. And the way I do it is by taking, so if I'm at X and I want the weight of X, I look at the Busemann, so Bx x plus E1, I'll call that the Busemann increment. So I look at the E1 increment and E2 increment and take the minimum of the two. And where is this coming from? Well, that's just the that equation, that induction that we saw earlier. All you have to do is just move the maximum to the other side. It turns into minimum when you actually combine terms, and then you use the definition and you get this. And one thing to learn from this also is, if you remember how we proved this relation, it's telling you how if you know the Busemanns, then you can actually construct the geodesic in somewhat a local way. So if you want to know where to go next from X, you look at the Busemann increment in the E1 direction and in the E2 direction, and you see which one is smaller, and you just take that step. Okay, so keep that in mind. All right, so there's another property which is called which is a monotonicity property that I'm not going to prove, but it's also, it has an elementary proof. And what's crucial in it is the fact that, so what is it about? It compares Busemann increments that are increments on the between nearest neighbor points, like x plus E1 or x plus E2, with different terminal points. So the terminal points, if you put the terminal points on the anti-diagonal, then you can use the fact that that's where two dimensions comes in. So you use the fact that to go from X to U, and to go from X plus E1 to V, these two paths have to cross. Okay, so you use that fact to prove the following inequalities between the increments. Okay, so one of the E1 increment goes one way, and the E2 increment has monotonicity the other way. Okay, so now, so a theorem that one would like to prove is the following. So let me encode the directions, the various directions in the first quadrant by this line segment between E1 and E2. So I'll call that U. And so what I want to prove is, if you give me a nice direction, so whatever nice means for the theorem to work, then if I actually calculate my Boozman functions with terminal point xn that is going in direction c as n goes to infinity, then these will converge almost surely. Okay, and then with that should come also a similar limit for the point-to-line objects, and there should be some relationship between the c and the h if you want the limit to be the same. So if I do the point-to-line and I pick the h carefully, then the point-to-line objects should also converge to the same thing that the point-to-point converge to. And the relationship between the c and the h is actually a convex duality relationship through the shape. So the h is, minus the gradient of the c. So this is not, this is sort of the kind of theorem that one would like to prove. And so let's see what this means first with the in relation to this Hamilton-Jacobi connection. So remember, you take n to infinity, that's like taking time to minus infinity. And therefore, this limit is actually like the global or by infinite in time solution that I've been looking for. And so this has been done by Lichier and Newman for a cousin model to last passage percolation. So first passage percolation just means change omegas to minus omegas. So instead of maximizing, minimize. But the key here is this word standard first passage percolation. So that's where the paths that you consider are nearest neighbor paths, not just upright paths. So all nearest neighbor paths. So they developed a technique for proving this, and they needed for the technique to work, they need a strong assumption on the curvature of the shape. So not just that it's convex, but some control on its curvature. I won't mention exactly what it is because we're actually going to try to start away from that, like making such assumptions. And so the way it's done is by proving actually existence and uniqueness and coalescence of so semi-infinite geodesics that go in the various directions. So you prove that for every direction that you choose, there exists so there exists a semi-infinite geodesic out of every point. There exists a semi-infinite geodesic such that if xn slides along the geodesic, xn will go in direction c. And those geodesics are unique. And if you look at the various geodesics out of the various points, then they all coalesce in the sense that they all merge together. Okay, and this coalescence then implies the existence of the Busemanns, because if, for example, if you're looking at these 2 points and you're trying to calculate the Busemann between them, well, remember, it's the gradients of passage times from these 2 points to the terminal point. So if you let the terminal point run along the geodesic, as soon as it passes the coalescence point, the difference stabilizes because it just becomes the difference along these passage times along these 2 branches, and the rest of the passage times cancel out. And so this was the way, like one way to prove existence of Boozman functions. Okay, so now about this condition on the shape, well, it's conjectured that actually fairly generally the shape should be differentiable, strictly concave, and satisfy whatever that curvature assumption was that was needed for the work by Licea and Newman. Okay, so what are models where you could verify this assumption? Well, in standard first pass percolation, there aren't any lattice models, but there's a model that has certain symmetry in it called Euclidean first pass percolation, and there you can just check. You get that the shape is actually a sphere and it's strictly concave, and the curvature assumption is satisfied. Also, there are some miracles happening in a certain last passage percolation model, the solvable case, where the weights are exponential. And in that case, you can calculate the shape explicitly and check that the curvature assumption works. And then you can carry out Newman's program and actually prove these results about the geodesics and therefore existence of Boozman functions. And then also there's a non-solvable situation that happens in the Burger's equation, but still with the special choice of the forcing, but still there's nice symmetries that allow you to conclude that the shape is quadratic, and therefore, again, Newman's approach works. And so what we want is actually to not make assumptions a priori on the shape. And so the way then is to start with the Boozman functions as the fundamental object instead of getting their existence from properties of the geodesic. And so that approach was taken by Damer and Hansen for standard first pass percolation and with general weights. And then by Georgiou, myself, and Timo Seppalainen for last passage percolation, again, with general weights. There is no need for the miracles that come from the exponential model in this case. So the way it's done is, well, you take limits in these Boozman functions that have the point to line, for example, Boozman functions, but you take it in the weak, you prove some tightness and you take it in the weak sense, and then you enlarge your space to put the limiting object on the same space. And you do that for enough directions. So you do that for simultaneously for a countable set of countable dense set of directions that happen to be differentiable points of G. And there exists such a set because G is concave. Okay, and so now the object that you get the limit, it has still the cocycle recovery and monotonicity properties because these were equalities, so they held in the almost sure sense, and this will push to the limiting object as well. Okay, so so now we have a limiting object for a bunch of directions that are in a countable dense set, but there's monotonicity. Remember, if you look at nearest neighbor edges only, then there's monotonicity in the endpoint, and that translates as you take a limit to monotonicity in the direction, and this monotonicity then allows you to take left and right limits, and then define an object for every direction. But then now it might be that the two limits on both sides are not equal, so you get two objects potentially. And again, the cocycle property extends to the limit and allows us to extend things to an object that's not only defined on nearest neighbor points, but further. And how does that work? Well, so the cocycle property, first, when I defined this limit, I defined it only for points that are of the form x plus ei, because that's where the monotonicity, where I have the monotonicity. But then the cocycle property holds for these objects in the following form, that if you add up and then to the right, the increments, and if it's the same thing as adding to the right and then up. And then if you define the bx plus eix as minus the bx plus ei, so if you're going backward, you just put the minus sign, then it allows you to, this and the cocycle property allows you to define the object b between any 2 points. Basically by saying, if I wanted the value between x and y, well, take any nearest neighbor path between the two and just add the values over the edges, the increments over the edges. And it won't matter which path you take because of the cocycle, the one cell cocycle property. Okay, so now the limiting object will have, again, the cocycle, so these BC plus minuses, both the BC plus and the BC minus, will have the cocycle properties, cocycle recovery and monotonicity. Just recovery and monotonicity just because they only dependent on stuff that is on increments that are in the nearest neighbors. So there's nothing really to check. It just passes from the B zetas having this property. Okay. And there is a consistency. So you might think, okay, what if I take a C originally in that dense set that I had before, that I had at the outset, and then take limits? Do I get like now 3 objects? And the answer is no. You actually get back, you can prove that you get back the objects that you started with. Okay, so now using the monotonicity, you can couple the point-to-line and point-to-point Busemanns with this limiting object that we just created. And you can prove that if the direction is nice, if the C is nice, so I'll say that one case that explains what nice means in just a moment. But if the C is nice, then actually there's no need for distinguishing the plus and minus. They're actually the same object, and the point-to-line and point-to-point Busemanns converge to that object almost surely. So that's the theorem that we wanted to prove that I mentioned before, that was proved before but, using the geodesics technique, but now there's no geodesics in the picture here. So for example, if you assume that the shape is everywhere differentiable, then you get that every direction is nice, actually, and you get that this limit holds for every direction. And if the shape has, like, for example, corners, then, well, in this case, you don't have a limit, but you can control the lim sup and lim inf of the prelimit objects using BC plus and BC minus, which will be different than in this case. And so this approach allows you to say more whether the shape is differentiable or not, but also notice that the nice theorem that says that there is a limit, so there is like a by infinite in time solution, does not need now curvature assumptions or even convexity or concavity, sorry, strict concavity. It just needs differentiability. Okay. So now we go to the geodesics. Since we got the Busemanns, we're going to do things in reverse now, and we're going to define paths using these Boozman functions. So remember how that recovery property was also telling you that if you follow the minimal increment, then you're following a geodesic. So what if we now try the following? Well, we have a recovering cocycle. And so what we are going to do is at every given point x, I'm going to follow, if I want, for example, the big C plus path, a path that corresponds to big C plus, then that starts at x, then what I'm going to do is I start at x and I look at the minimal increments of big C plus, so going to x plus E1 or x plus E2, and I follow the smaller of the two. And I can decide on a tie-breaking rule if they're equal. For example, I always take E1. Okay, and so then you get a path, a semi-infinite path, starting at whatever point you want. And it turns out that the cocycle and recovery properties imply that this path that you get is actually a geodesic. So now there's a machine that out of the Busemanns creates geodesics. And using that, you can prove the following theorem. For almost every choice of omega, so you throw away one null set, and then the following holds. For every x, these Busemann geodesics are directed in the various facets of this sublevel curve. So the sublevel curve is a convex curve because G is concave, but it might have flat segments. And so you get actually geodesics that are directed in the various, that's really what the theorem, what this sort of mathematically says, that for every facet you get, there is a Busemann geodesic that gives you a, that is directed inside that facet. Okay, so that's an existence result. Okay, so then these curves, because of the monotonicity of the Busemanns, these curves are actually ordered in the way you'd expect. Okay, so so because of that, that means, and the uniqueness of the finite geodesics, because of the continuous weight assumption, you can trap any geodesic starting at x, you can trap it between an xc plus and xc minus for some xc. Okay, you can't just keep interweaving, go in and out, because then you'll have like minimum two minimizers between, or maximizers between two different points, and that's not allowed by the continuous weight assumption. Okay, and then now you combine that with the previous theorem, and you get that almost surely. So you throw away again one null set, and almost, and then for omegas in the rest, all geodesics are directed into at most the union of two facets, two neighboring facets, because the C plus was directed in one facet, and the C minus was directed in the facet right next to it, and so you get that every geodesic is directed at most into the union of two linear segments. And now, if you throw in also an assumption that G is strictly concave, then there are no linear segments, and so or you could say the linear segments are actually degenerate. And so, in fact, you get that every geodesic, almost surely, every geodesic has a direction. Okay, so this result did not only needed strict concavity, did not need any curvature assumptions. Okay, so here's a different type of results. So on the previous slide, the results were of the form, almost surely something happens for all directions at once. Now, here's another type of results. For every direction you fix, we get the following, almost surely. So I fixed the C, and then the Busemann C plus geodesics, the Busemann geodesics that are created by the big C plus coalesce, and the ones that are created by the big C minus coalesce. And coalescence, again, is it just means that if you start at two different points, then the geodesics merge. Okay, so now here's so if you now assume that the shape is differentiable, then you can prove also that there's no distinction between the plus and the minus. So that's something I mentioned already before. And putting these two together tells you that Well, if G is differentiable, then there is a unique geodesic that's directed in every facet of the limit shape. Okay, so for every facet of the limit shape, you fix that facet, and there is a unique geodesic that goes into that facet. Okay, but now the null set in these kind of results might depend on the direction. And so what we want is we want to look into the uniqueness and coalescence for all directions at once, and that means that I want to switch around the for all xi and the almost for almost every omega. Okay, so here's the tool now. So if and so suppose I have a situation where out of x and y, I draw the xi geodesic for some direction xi, and they happen to coalesce, and they coalesce at the point z. Okay, so then we argued before that the Busemanns, when you calculate the Busemann direction xi, that's just the difference of the passage times from x and y to z. But then now suppose I tell you for some reason that this quantity is actually constant over an interval of x's, then that tells you, because this doesn't have a xi in it, and because of the continuous waste assumption, that tells you this picture here, the portion of the paths that go up to z, that should not vary as you vary the xi. So the portion of the geodesics, the xi geodesics, you vary the xi, but the initial portion of them remains constant. So that gave us the idea of looking at the following. So you look at the Lebesgue-Stieltjes measure that corresponds. So you fix x and y, and you look at the whole process of the xi. I'm omitting the plus and minus because these are left and right limits. And so remember these things, because of monotonicity, this object is really just a sum of monotone functions. So that's another reason why it's screaming at you to like define this Lebesgue-Stieltjes measure. And so then look at the support of this measure and take a union of the support of this measure over all pairs. Okay, so this is a random set. What's the properties? What are the properties of this random set? So if you are not in this random set of directions, so if you're not an exceptional direction, then there is coalescence, and there's no distinction between plus and minus. And if you are on this set, then there's a problem with uniqueness and coalescence. And so let's look at a special case. So if the G, the shape, is differentiable at the endpoints of its linear segments, so that means that when you draw this curve, this level curve, every time you have a linear segment, is smooth on the endpoints. So that's an assumption I'll use. I'll call it star. So for example, this holds if the shape is always differentiable, or if it's strictly concave, so there are no linear segments. Then, under this assumption, you can prove the following, that with probability 1, so the previous slide was talking about the Busemann geodesics, coalescence and uniqueness for the Busemann geodesics in the various directions. It said that there is a problem with the coalescence if you're in exceptional direction. But now, under this assumption, because you can squeeze geodesics between xi plus and minus geodesics, you can extend this to saying that actually being an exceptional direction means that there is a problem with being not an exceptional direction means that there is a uniqueness and coalescence of the xi directed geodesics that are directed in the facet that contains the xi. So this set of directions, really, this set of the support nu omega is the set of, you can think of it now as the set of directions where there's a problem with uniqueness and coalescence. And no, well, maybe it's empty. But the answer is no, it's not empty. It's actually dense away from the linear segments of G. And so there's a lot of directions like this. They're random, but it's also not too big, because the complement, it's a complement of, or the complement of this set is the countable intersection of dense open sets. And some familiar members of the set are the directions of the composition interfaces. So if you draw the tree of geodesics from X to the various points, and you look at the interface between the trees rooted E1 and E2, then that interface has, under the nice assumption, it has a random direction. It has a law of large numbers. And that direction is the unique can be shown to be the unique direction for which the plus and minus Busemann geodesics separate right away at x. And if they separate, they can't reunite again because of the unique, because of the continuous waste assumption. And so in this direction, you can see that there's a problem with the coalescence and with uniqueness. And so that direction is actually is part of the exceptional direction set. And so here's a simulation in the exponential case. These are the two geodesics. And this is the competition interface. And so here's a lemma that tells you that when are these directions of competition interfaces the only bad directions, the only exceptional directions? Well, that's if the Busemann process happens to be a jump process. And that is an analytical way to say it, but there's a geometric way to say it, and that is when the Xi plus geodesics coalesce and the Xi minus geodesics coalesce. If you can guarantee that always happens, then the only members of the exceptional set of directions are the competition interface directions. So the picture would look like this: the Xi plus coalesce, the Xi minus coalesce, but Xi is an exceptional direction. So the Xi plus and the Xi minus, they're different. Okay, so special case is in the exponential model, and that's for the next couple of slides, which is what's left. In that case, you can calculate explicitly the shape function and check that the nice assumptions that it's a very nice function. And in that case, many computations are possible. And recently, Timo, Seppalainen, and Louis Fan actually characterized the support of those sets, and they turned out to be the support of these measures. They turned out to be union of Poisson processes. In particular, this is a jump process, and so the set of exceptional directions is just the competition interfaces. And one more result to just get the theorem that is going to be on the next slide. It's so a result by Coupier from 2011 that says, well, there isn't any direction, random or not, in which you have 3 or more geodesics. So you put now all of this together, and you get that the following holds almost surely. For the exponential model, you throw away a null set, and you get that the exceptional sets of directions, well, we define it as the jumps of the Busemann process, but it's also the set of competition interface directions. So it's countable, and it turns out to be dense. If you are not an exceptional direction, then there exists a unique geodesic in that direction out of X, and all these coalesce. And if you are in that set of directions, there exist exactly 2 geodesics that are directed in that direction. And these are exactly the Busemann ones. And the plus ones, so the leftmost ones and the rightmost ones, they coalesce together separately as 2 separate sets of geodesics. And that's it. There are no other geodesics, semi-infinite geodesics. And so, so here's the graph now, just to describe that red graph that was before, that I mentioned on the slide at the beginning. So consider the following graph on the dual lattice. So for a direction that's an exceptional direction, therefore there are some sites for which there's issues with coalescence. And so on the dual lattice, put an edge if the transversal edge on the original lattice has different big C plus and big C minus, which means that the leftmost and rightmost geodesics, so the Xi plus out of X and the Xi minus out of X plus E2 do not coalesce. And we do the same for the vertical. And then that graph, so now you have a graph on the lattice, and that is related to the instability that I showed you. So I'm just going to run the beginning of this video quickly, just to remind you. These are, so what's going on now is, we understand now what's going on, right? Because this is the geodesics out of E1 and E2 are either all of a sudden the Xi plus, they're stabilizing at the Xi minus for a while together, so they're coalescing, or the Xi plus, so they're coalescing, or they're one of them is the Xi plus and the other is the Xi minus, and they're not coalescing. and they keep switching between these states. So properties of this graph: it has zero density. The picture is not ergodic because I'm looking at the random direction. So even though the graph exists, it has zero density. And it's bi-infinite. It has on it bi-infinite paths that coalesce in both going up and going down. So it is this picture. And here's a zoom in, where the green and the yellow are the Xi plus and Xi minus geodesics. And you see that the graph is where they potentially separate. So on this graph, if you take a point in here and a point in there, eventually, if you run further, like up high enough or down high enough, there will be paths that coalesce. Okay, so one very last quick thing, we can actually even calculate some statistics. So if you condition on this red graph going through an edge, like the 0, E1, that has probability 0 of happening. But if you condition it in the palm sense and you look at what are the locations of the other jumps, the crossings of the graph, well, they turn out to be the zeros of the zero set of a simple symmetric random walk. And we have no idea why this connection is true other than actually doing the computation. Okay, so that ends my talk. Thank you.